Okay, last set of video notes for the kinematics unit. We're going to finish up by talking about projectile motion, which you studied last year, which is usually one of the harder topics in Regents. And the reason it's hard is not because the math gets much harder, but just there's a lot of stuff to keep track of. The more you practice with projectile motion, the more you practice identifying what variables you know, how you can solve for the ones you don't, the easier it gets. So really you do want to do a lot of practice with this sort of stuff. What is projectile motion? Projectile motion and free fall are the same thing. I like to differentiate projectile motion. I don't know if it's totally accurate to do so by saying that instead of for free fall, usually we think of things just falling straight down, although projectile motion, like I said, is free fall. When something's in projectile motion, I like to think of it as we definitely have an object moving in two directions, both the x direction and the y direction. So it is a type of free fall in which an object is thrown or kicked or launched or whatever, and it now has both vertical and horizontal motion. The key thing is projectile motion, the assumptions of projectile motion only work when the only force on the object is gravity. So while the object is getting thrown, while it's in the hand, or while it's getting kicked in contact with the foot or launched or whatever, it is not yet in projectile motion. Once it is away from the whatever is causing it to move, and gravity is the only force on it, now it's in projectile motion. Okay, so it's got both vertical and horizontal motion. Now, how do we deal with this? Okay, because this is confusing. There's a lot of stuff to do. What we're going to do is we're going to group the variables into x's and y's, x variables and y variables, and deal with them separately. One of the biggest stumbling blocks I see to people being successful on projectile motion questions is they don't want to list their variables. They don't want to take the time to write out what they know and what they're looking for. My opinion is if people do this, if people learn to get in the habit of doing this, then it makes the problems a lot easier. First, question number 1. A ball is thrown off of the edge of a building at a speed of 5 meters per second. If the building is 13 meters tall, how far away from the building will the ball land? So first thing, let's just draw a picture of this. Okay, here's our building. We want to know where the ball lands. We do know that the building itself is 13 meters tall, and we know that the initial speed of that ball is 5 meters per second. What we should also do at this point is just draw a little axis, because this might help us with if something is going to be positive or negative. So here's x, y, and let's assume, well, actually, we'll get to that. What I would do at this point, once I've gotten my little picture drawn and the things that I know labeled, is I would immediately start to break up my variables into x's and y's. And sometimes one of the stumbling blocks is people don't remember. They're like, well, what am I supposed to know? What do I know based on what they tell me? What can I just kind of assume? The variables are going to look very similar all the time. If you think about it, we're going to treat x's and y's completely differently. We might have a use for, the initial position. We might want to know the final position. Matter of fact, that is what we want to know. We want to know what the final position is. And as far as the initial position goes, we might as well say that, since it doesn't tell us otherwise, it starts at x equals 0 meters. Helps us cancel something out. We might want to know the initial speed, or initial velocity in the x direction. As a matter of fact, we do know that. We know that that is 5 meters per second. You can see I just put like a little x here, so I know I'm talking about the initial speed in the x, or velocity in the x direction. I might want to know the final velocity in the x direction. I'm going to come back to that one in a second. Most importantly, because this is the same for all projectile motion cases, I want to talk about the acceleration in the x direction. Remember that in projectile motion, the only force acting on the object is gravity, and we know that gravity points straight down. So the only force on this object is pointing straight down, which means the only acceleration this object has must be in the vertical direction, in this case the downward vertical direction, which means since there's no forces in the x direction, there cannot be any net force in the x direction, which means no acceleration in the x direction. In projectile motion, the acceleration in the x direction is always 0 meters per second squared. In other words, the velocity in the x direction does not change. So the initial velocity and the final velocity in the x direction are both 5 meters per second in this case. In the y direction, we have the same exact set of variables, except that we're talking about y's, the vertical variables instead of x components. Yeah, y naught y, v naught y, vy, ay, and time isn't really either, so I'm going to throw that down there. We don't know how much time this takes for the ball to go down this way. But as far as the initial position goes, it starts 13 meters up, so we might as well say that the initial position is 13 meters. It ends up on the ground, so we might as well say that this is 0. And that makes sense too, as going from y, the final spot on the ground, up here, we're going in the positive y direction, and we're gaining position. Our y naught is 13 meters up here, so that makes sense. Let's see. The initial velocity in the y direction. This object got thrown horizontally. So did it have any vertical motion to start with? No. So the initial velocity in the y direction is 0. Do we know the final velocity in the y direction? No, not yet. That might not even be important though. Sometimes people get confused about what they know and don't know and what they have to solve for. There might be cases where you don't have to know everything to solve for it. Once you have enough to solve for what you're looking for, just do it. Okay? Don't bother trying to find every little thing. And the acceleration in the y direction, this is an object in free fall, and we know that objects in free fall accelerate at the acceleration due to gravity, which is 10 meters per second squared downward. So I'm going to put, since up is positive in this case, I'm going to put negative 10 meters per second squared. All right, that's a list of everything that I know. Notice that I was only given 2 numbers. I filled in like 6 other things, okay, just based on logic and how we, some more analysis. The accelerations, I recommend filling those in first. Those are always going to be the same in projectile motion. You know that the velocities in the x direction are always going to be the same. It's very easy usually to say what the initial positions are, and some other things might also be 0 based on the context. Now it's up to us to solve for how far away from the building will the ball land. That's this right here, x. So I've got a decent amount of information in the x direction. Might as well try and just solve for it directly. Maybe I only need to use one equation here. I'm going to go with this equation. X equals x naught plus v naught x t plus 1/2 ax t squared. Now I know the initial position is 0. I know the initial velocity in the x direction is 0. So what I'm left with is x equals 1/2. Oh, geez, I did that wrong. Big mistake. This is not 0. The acceleration in the x direction is 0. Got ahead of myself. What I'm left with is x equals v naught x times the time, which is great. I'm looking for x. I know the initial velocity in the x direction. The only thing is I don't know the time. Okay? That doesn't mean this equation is wrong and you shouldn't use it. It just means if you can find the time somehow, maybe that then, if you could do that, then you would be able to use this. So let's try and find the time. And if you remember from last year, one of the best ways to find the time, 90-95% of the time, you're going to be using the y variables. I'm going to use the exact same equation just in the y direction. So y equals y naught plus v naught y t plus 1/2 ay t squared. Now this time I have, let's see, y naught is 13 meters. Y, because that's when it hits the ground, is 0. Initial speed in the initial velocity in the y direction, that's 0, plus 1/2 times negative 10 meters per second squared multiplied by t squared. So this ends up being, let's see, I subtract a 13 to the other side, so I get 13 equals negative 5 t squared. I divide the negative 5 over to the other side, so it's just 13 divided by 5. And then I take the square root, and I get a time of approximately 1.61 seconds. Okay? I come and plug that in over here. The initial speed was 5 meters per second, or the initial velocity in the x direction was 5 meters per second. The time that it was in flight for was 1.61 seconds from where it was launched till it hit the ground. And I get that the object traveled 8.06 meters. Okay, so that's how far this object went before it hit the ground. Now, the neat thing about this is you can go and test this. If you were to go to the top of a 13 meter tall building and throw an object off at 5 meters per second, it would land approximately 8.06 meters from the base of the building. This is something you can test. This is why I love this type of projectile motion. Now, could I have done some things differently? Sure. Could I have made my axis different? Yes. Could I have made my origin different? Yes. Would I still get the same answer? Absolutely. Okay, and I encourage you to try that. Okay, if you don't get the same answer, you've got something else going on that's wrong. Next question. A bullet is fired from a gun at a target 60 meters away. Initially, the gun was aimed so that it was level with the center of the target. However, the bullet struck the target 0.1 meters below the center. What is the initial horizontal velocity of the bullet? Well, this is kind of weird. Why didn't the bullet hit the center? Because it was traveling and it was subject to the force of gravity pulling down on it, making it accelerate down. So because the bullet does not travel instantaneously to the target, it drops a little bit. What we have here, here's where the bullet was fired from. Here's our target. And it went down a little bit. The amount that it went down, 0.1 meters. Okay. Now, for my axis this time, I'm actually going to do this. I'm going to change it up a little bit. Okay. Here's x, here's y. These are the positive directions. So I'm saying downward is positive direction for y. Okay, so let's list out our variables again. You'll notice it's the exact same thing as before. X naught, x, v naught x, vx, ax, t, and then y naught, y, v naught y, vy, ay, and we want to know what each of these is. Okay, or just enough so that we can solve for what we're looking for. We are looking for the initial horizontal velocity of the bullet. That would be v naught x. Now, what do we know? Let's start with the accelerations. We know in every projectile motion problem, the acceleration in the x direction is 0 meters per second squared. The acceleration in the y direction is 10 meters per second squared. This time it's not going to be negative though, because look, I made my axis point down for positive y. So this is just going to be 10 meters per second squared. The object was fired horizontally, which means that the initial vertical velocity is 0. I don't know how fast it's moving at the end, so I'm just going to put a question mark next to that one. The initial y position was 0, and then it moved down 1. Okay, we might as well just say it started from 0, 0, and then it moved down 1/10 of a meter. And down is positive, so we're going to say the final y position is 0.1 meters. The final x position, it starts at 0 meters, ends up 60 meters away, so that's 60 meters. We don't know v naught x or vx. Okay. Now again, how are we going to solve this one? Oh, we don't know the time either. Okay. We want to know the initial horizontal velocity of the bullet. Let's try the same approach we did last time. X equals x naught plus v naught xt plus 1/2 ax t squared. In this case, we don't know the initial, or we know the initial position is 0. We know it's not accelerating at all. We're back to this. We know what x is, except we are looking for v naught x. We don't know the time. But again, if we can find the time, then that's not a problem because we know that the final position is 60 meters. Let's try and find the velocity or the time doing the same example of what we did before. We know how far it drops. We should be able to figure out how much time it would have taken for the object to drop that much. Now we know the initial position in the y direction is 0. We know the initial velocity in the y direction is 0. The final y position is 0.1 meters, 1/2. The acceleration in the y direction is 10 meters per second squared, t squared. 1/2 times 10 is 5. Divide the 5 to the other side, so 0.1 divided by 5, 0.02. I take the square root. I get that in order for the bullet to drop that far, the time must be 1.41 seconds. I plug it in over here. I divide 60 by 0.141. Big difference. Let's just rewrite that. 0.141 seconds. I divide that to the other side. So 60 divided by that. Let's just do the whole thing. 1 divided by 5, take the square root, divided by 60, inverse. So I get that the initial velocity is approximately 424.3 meters per second. Now, is that about correct for an object getting fired out of a gun, a bullet getting fired out of a gun? Absolutely it is. Okay, absolutely. So, even if the problem looks a little strange, you can still figure out, you can still just use kinematics principles and projectile motion to figure out how fast it must have been going. Okay? It wasn't a big deal that we couldn't find it using just one equation. Sometimes you have to use 2 or even 3 in cases like this. Alright, this next one we're going to find a whole bunch of stuff. A rock is thrown off a cliff, takes 4 seconds to hit the ground. If it lands 40 meters away from the base of the cliff, determine the initial horizontal velocity of the rock, the height of the cliff, and the velocity just before the rock hits the ground. So again, we have a situation like this, where we've got a rock, gets launched, we don't know how fast, it does hit the ground though, and we know how much time, we know how far away it lands, 40 meters. Let's see, what else don't we know? We do not know the height. Okay, so here's what we're going to do this time. We're going to list out everything that we know, just like we did before. Let's put an axis on here. Let's do our standard axis. X, Y. Okay, might as well say that x naught is 0 meters. We know that it ends up at 40 meters. We don't know the initial velocity that it was launched with, which means we also don't know the final velocity that it has, but they should be the same. We do know that the acceleration is 0 because there are no forces on it in the x direction. Okay, that's standard whenever you have a projectile motion question. We do know the time this time, which is interesting, 4 seconds. For the y's, we don't know the initial height, so I'm just going to put a 0. We do know it ends up on the ground, so that's what we're going to say. We'll say it ends up at y equals 0. Since it was launched horizontally, we know that the initial velocity in the y direction is 0. We don't know the final velocity in the y direction, but we do know the acceleration in the y direction. Looking at this, our up direction is positive, so the acceleration must be negative 10 meters per second squared. Okay. And I know I've used basically only one of the kinematics equations so far, and that's because a lot of times it seems like that equation gets used more often than the others. I know that there's also v equals v naught plus at. I know there's also v squared equals v naught squared plus 2a, and then in parentheses x minus x naught, but we're not going to, a lot of times, I'm not saying you will never use those, but a lot of times this equation seems like it comes out to be the one that's used the most, at least in the problems that you guys will get. So, let's figure out let's figure out some of these problems. Determine the initial horizontal velocity of the rock. Well, we know that since there's no acceleration, this is actually an object that in the x direction, it doesn't change velocity. In other words, it's at a constant velocity. And since it's at a constant velocity, that means that the velocity in the x direction is equal to the initial velocity. We can just say that the velocity in the x direction must be equal to the change in displacement in the x direction divided by time. Okay, and just so you know, I could have gotten this result by using this equation up here and then rearranging and simplifying, but if you know that, I mean, it's constant velocity, you know, why go through the bother of doing all this? Why not just say, hey, the velocity in the x direction must be equal to the change in displacement over time. So what I get here is, let's see, so x naught is 0. So this is 40 meters over 4 seconds. The initial velocity is 10 meters per second. Makes sense. Something moves for 4 seconds and moves 40 meters. It must be moving 10 meters per second. Great. What about the height of the cliff? Well, let's see. It falls for 4 seconds. This one should be pretty straightforward. We know the final position is 0. We know the initial velocity in the y direction is 0. We know that the acceleration in the y direction is negative 10 meters per second squared. The time is 4 seconds. Okay, so what that means is 0 equals y naught plus 1/2 times negative 10, is negative 5, times 4 squared is 16, is 80. So 0 equals y naught minus 80. That leads us to y naught equals 80 meters. Great. We've got the height of the cliff. The last thing we want is the velocity just before it hits the ground. And notice, we did not say the velocity in the x direction or velocity in the y direction. We know the velocity in the x direction is 10 meters per second. We don't know the velocity in the y direction yet, but the velocity in the y direction isn't our final answer anyways, okay? So how are we going to find that velocity in the y direction? The easiest way would probably be to use this equation. Vy equals v naught y plus ay t. The initial velocity in the y direction is 0. Vy equals negative 10 meters per second squared times 4 seconds. Vy equals negative 40 meters per second. But that's not what we're looking for. We're looking for the overall velocity. That means not in any one particular direction, just overall. When this thing is about to hit the ground, it's moving both horizontally and vertically. How do we find the overall velocity? Look what I have here. I have an x component, a y component, and I'm looking for the overall velocity. I can use Pythagorean theorem. I should be able to find this by doing v squared equals vx squared plus vy squared. If you're asking where that comes from, imagine that I just wrote a squared plus b squared equals c squared. That's pretty much the same thing. So v squared equals the velocity in the x direction at the end is 10 meters per second, because that didn't change. The velocity in the y direction is 40 meters per second. I know I'm kind of squeezing this writing in. Hopefully you can read it. If I do 10 squared plus, let's see, 40, negative 40 squared. Oh, that didn't work. 10 squared plus 40 negative squared, and parentheses, 1700. I take the square root. I get that the overall velocity is 41.23 meters per second. And you could say that, hey, maybe we need the direction as well. I'm just going to leave that there. I should have wrote in for the that we want the magnitude of the velocity. So far this has all been problems where we're just launching something horizontally. Next we're going to look at when we launch something at an angle. There's many different types of projectile motion questions. Some will be similar to this. Some will be a little bit different. The more you see and the more you practice and give an honest effort to, the easier these questions will get. Be right back. Actually, okay, good. There, you should be able to see everything. Now we'll be right back.